I suggest we get started. Welcome everyone to this month's installment of the Athena Science webinar. We're very happy to have with us Vittorio Ghirardini, who is currently at MPE, but before that he did his graduate studies, both bachelor and master's in Trento in Italy, and got a PhD in Bologna in astrophysics. He then spent a short time as a postdoc at the Harvard Smithsonian Center for Astrophysics, working with Esra Bulbul. As Esra moved to MPE to spearhead the part of the Rosita team, Vittorio was very happy to follow her, and he has been working on the Rosita All-Sky survey, and in particular, the final equatorial depth survey. And he will tell us today about clusters of galaxies, and in particular, the evolution of the entropy profiles of clusters of galaxies with redshift. So Vittorio, thank you very much for joining us, and the floor is all yours.
Thanks a lot, Aurora. Thanks a lot for the nice introduction. And just to make a small punctualizations, as of 1 month, less than 1 month, I've been joining actually back in Italy, the INAF National Institute for Astrophysics in Bologna. So I come back full circles and go back to Italy. But still, I'm going to, I would like to still to thank for giving me this very nice introduction and the opportunity to give to all of you like an overview of what is the entropy evolution in galaxy clusters, which is a topic that was kind of very dear to me, since it was like one of the first topics that I encountered doing my PhD. It's also like a main topic that I followed also like later in my first postdoc. And then it was a good adventure to take back all of this and do like a nice review and put everything together. So thanks a lot for that. So let me start by introducing the topic of this kind of conversation, which is galaxy clusters. So when you look at an image of the sky, and you see, of course, you see a lot of galaxies, like the cross one, like you see here, for example, and this is an image from Hubble. However, if you look beyond the stars, you see a lot of galaxies. You see a plethora of background galaxies, and in some places of the sky, you see like there are more galaxies than compared to other places. Like, for example, you see that in this region here, there is way more of these galaxies than, for example, here to the other side of the image. And it was indeed how galaxy clusters were first discovered already in the 18th centuries. However, later on, during the 60s, after the launch of the first X-ray satellites, the 60s of the last century, it was discovered that there is a space filling plasma that is filling all the space in between all of these galaxies. And for example, here you see the case of Coma cluster, which is a very well-known local galaxy clusters. And you see the SDSS images in the background, which is all the galaxies that made up these clusters, and also galaxies in the foreground. And this purple bluish emission that you see in front, in between in all of these galaxies, is the X-ray emission that in this case is observed by XMM Newton. So it's a very other good way of observing galaxy clusters through X-ray. And also galaxy clusters have a very nice signal that they leave into the radio waveband, for example. And here's also the case of a Coma cluster observed by LOFAR. So you see that also in radio, galaxy clusters shine very bright. And there are also other wavebands in which galaxy clusters shine. And I'm going to talk a bit more later on during my talk regarding, for example, how galaxy clusters shine in a Z, for example. But this just to introduce a little bit the topics. So what are these galaxy clusters that we see today? How do we connect them with a theory, with cosmology in general, with how the universe is forming and evolved? So if you take a look at some simulation, at hydrodynamical simulations, and you have that when cosmic time passes, you form structures, and particularly at the nodes of the cosmic web where these filaments intersect, you find that there is a lot of material, and is actually corresponds to this galaxy cluster that I was showing you before from observations. So you can see here to the top an evolution of a density field of the universe in the simulations of in the paper by Krasov and Borgani in 2012, where you see this density field that evolved from a redshift of 3 to the redshift of 1, and you see that you formed these objects in the center, which are the known galaxy clusters. And just to give some numbers regarding them for the general audience, you can see, I just say that galaxy clusters are generally among the most massive virialized structures in the universe. So they have 10 to the 14 to 10 to the 15 solar masses as a rough number. They are very large on the plane of the sky. I mean, physically they are very large. They are like 1 to 3 megaparsec away. And also they are formed very recently. As you see from above here, you see the redshift of 3. You basically don't have much of a density, but already a redshift of 1 here, you see a lot of these whitish, more dense regions. And galaxy clusters are generally dominated by gravity. And for this reason, for this very good connection with gravity, they can really be used as cosmological probes. But they also are very important in order to assess several interesting astrophysical phenomena, for example, AGN feedback, cooling, and so on. And galaxy cluster has shown to be very, very important, especially for cosmology, because the number of clusters that we see in the universe, it's strictly a prediction from cosmological model. Like if you count clusters as function of mass, for example, and that is distance from us, then the number of clusters that you see, as you can see here from the left-hand side when you see the Helio mass function, is depending a lot on cosmological parameter, for example, in this case, omega matter, and connecting the theory of the cluster number count or the mass function with the observation, like you see, for example, here on the right-hand side, an image taken from a Rosetta Sky survey, we see the detection of all the clusters that were used for cosmological analysis, then you get a really powerful cosmological probes. And indeed, that is what we in the Rosetta collaborations, we did until, and in February this year, we published our result here in orange, which showed to be extremely competitive compared to other results. Like you see here, Planck CMB in blue, you can see SPT galaxy clusters in green, you can see in gray cosmic shear results from DES and KIDS, or you can see here in purple the Bayer relative space distortion from SDSS of a couple of years ago. And so, yeah. And galaxy clusters indeed are very nice because of the connection with cosmology. However, how you connect theory with the observations is very much dependent on the astrophysical properties of galaxy clusters, as mass is not directly an observable that we can directly get from galaxy clusters. And therefore, connecting the observable that we get, which can be luminosity, can be temperature, can be count rate, can be any other actual observable we are able to measure from galaxy cluster, and its link with this observable and mass, which you expect here on the right-hand side term, it's really a very crucial and fundamental term that we need to understand in order to do and perform precision cosmological analysis, as indeed it was shown several times that the connection between mass and observable is a dominant source of systematic in cluster cosmology. And so understanding the astrophysics behind the connection to mass and observable is fundamental in order to go in that direction. Entropy, it's an interesting quantity, and it's also linked to not just, for example, cosmological information, but is also linked, for example, to structure formations. Since clusters being young objects, they are still accreting material at high radii, and this accretion at high radii can really be visualized thanks to the entropy, as entropy is a quantity, a thermodynamic quantity that is really sensitive to changes in heat of the system. But of course, galaxy clusters can also be, and entropy can also be very useful in order to study astrophysics in terms of what happens in the core of clusters, which are among the most energetic phenomena of the universe, which involve the AGN feedback and cooling balance, basically. But also in the outskirts, you can also have presence of magnetic field, presence of accelerated electrons, and this induces some relativistic electrons being accelerated and producing synchrotron radiation, which we can see as was shown before in radial. And overall, at large radii, galaxy clusters are not expected to be yet fully in equidistatic equilibrium yet. And so there should be a lot of non-thermal phenomena that are affecting the outskirts of galaxy clusters, which are very important in order to take into account, as the volume of galaxy clusters that we can probe in the outskirts, it's very significant. And so probing a large amount of volume of galaxy clusters enables us also to measure very precisely also its mass and therefore the connection with cosmology, for example. So as I was illustrating in my first 3 slides, we can see galaxy clusters through many different methods. So we can look at their galaxies, the member galaxies of galaxy cluster, like you can see on the left-hand side, the chroma clusters seen by SDSS. However, these galaxies only made up roughly 5 to 10% of the baryon content in galaxy clusters, so not really much of the matter we can actually study in galaxy clusters is actually into galaxies, despite the name. And on the right-hand side, you see the radio emission, which also in the case for coma, and the radio emission is caused by these relativistic electrons, which are pass through a magnetic field, and basically we see them through synchrotron radiation. But these relativistic electrons are really a very minuscule fraction of the overall matter content in galaxy clusters. And the vast majority of the baryons, the matter that we can, the visible matter we can actually study in galaxy clusters is in the so-called intercluster medium, or ICM, which comprises roughly 85% to 90% of the total matter content in galaxy clusters. And this leaves a very good and interesting signal in X-ray and SZ, that I'm going to talk about in a couple of slides. So just a few properties on what this intercluster medium is. So it's a very hot gas. Its temperature is 10 to the 7 and 10 to the 8 Kelvin, so it's very, very hot. And at this temperature, this gas is basically fully ionized, which means there are a lot of ions and a lot of electrons. And once an electron sees an ion, it gets some acceleration and emits radiation through Bern-Strahlung. Further, ionized electrons sometimes recombine, and therefore also produce a lot of recombination lines, which can really be seen in X-rays. And this gas, containing a lot of free electrons, is also leaving an imprint in the millimeter waveband on the CMB through the so-called Tanya-Wiedź effect. And since this gas is very diffuse, very tenuous, it's not very dense at all, it's 10 to the minus 3 to 10 to the minus 5 particles per centimeter cubed, it can really be considered almost an ideal gas, where you just need to know a couple of thermodynamic quantities like density and temperature or density and pressure, and you can use those to get all of the other quantities of interest, for example, entropy. So in X-ray, the signal of the X-ray you can see on the top hand side here on the title of the slides, that depends on the density square and on the cooling function. So it depends a lot on the density, which means detecting clusters in X-ray really enables to detect bound systems as the signal equals with density squared. And this enables to find objects that are more concentrated, that are a higher signal to noise ratio compared to the background. So they have a high contrast with respect to the background, and compared, for example, to optical galaxy overdensity, it's much easier to find and characterize galaxy clusters in X-rays. And the same characteristic that allows this detection also enables to build very simple flux-limited samples. We can really be used to build up super simple tools. It can be used to build a simple selection function, because a selection like this is going to be easy to model. And further, all the observable that we get from galaxy cluster, luminosity, temperature, gas mass, or many more, are really tightly correlated with mass. And therefore, going back to the connection I was mentioning before between mass and observable as a fundamental quantity to understand for cosmology, it's also an ideal method of study this relation using X-rays. And furthermore, the the overall information that one can get from X-ray on galaxy clusters is very large, because we don't just get information from imaging them, like you can see here on the left-hand side, the image of Hubble 3236 in air zeta, but you also see these images or these photon counts as function of energy, which gives us a very good amount of information on the overall metal content in galaxy clusters. As you can see here, over the image, you see in yellow an example of a spectra of galaxy cluster, and you see that there are very bright lines that we see in the spectra, and therefore X-ray observation of galaxy cluster are really powerful in order to assess the metal content of galaxy clusters. However, one limitation that one always have to remember is the dimming effect of X-rays of brightness with redshift, as its signal goes down with luminosity distance squared, so it's going to be very dim at higher redshift. On the other hand side, you have the ACM is leaving an imprint of the CMB, as I was saying before, because you have these free electrons that are very energetic and are impacted by the background CMB photons, and these electrons give a little bit of their energy to these photons. So the CMB photons have their energy being increased slightly, and this produces a slight shift in the CMB spectrum, as it's visualized here to the left image that you see here. And the nice advantage of the signal is the fact that it's independent on redshift. However, this signal is just dependent on simple density times temperature, so it tends to be weaker than X-ray signal. However, in the last decades, thanks to the advance of modern and very sensitive SZ instruments, like Planck, ACT, SPT, or LICA2, for example, it's very possible to measure significant amount of signal from galaxy clusters and actually do even cosmological inference using the cluster detected in SZ because of that. Okay, so the final topic I wanted to introduce in this conversation is regarding the entropy. So entropy is defined as just as the ratio between temperature and density to the ratio between temperature and density to the 2/3, or pressure divided by density to the 5/3, and the connection between the two is just the simple gas law, where pressure is density times temperature. And I wrote both of these equations here because I think it's important to remember that if one has access to X-ray information, one has directly access to the density of the gas, and by doing spectral analysis has access to temperature information. So if one has X-ray on information, one will use mainly the equation here to the left-hand side because it combines these two quantities to get the entropy. However, if one has a Z signal, as the Z signal is proportional to density times temperature or the pressure of the gas, in a Z one can only get the pressure. So you kind of always need also an X-ray quantity, which is like density, for example, which is a cheap quantity to obtain. And therefore, by combining pressure for a Z and density from X-ray is also a very powerful tool to recover entropy in galaxy cluster. And if one has a combination of both X-ray and a Z, using both of these equations is a very powerful tool to actually probe and measure the entropy and its profile. And entropy is very important in order to study galaxy cluster, especially the thermodynamic history of clusters, because every time you introduce some heat in the system, you increase entropy, and every time cooling takes away some heat from the system, your entropy will decrease. So before going into the observation, I will going to give some theoretical background regarding what are the entropy profiles in galaxy clusters, what do simulations tell us. So since the early 2000s, it was very well known that if gravity is the only active force in the formation of galaxy cluster, in building up the galaxy cluster and its properties, then the entropy profile should follow a simple power law relation, like radius to the 1.1 relation that you can already see here. And plus, being cluster self-similar, using some particular scaling, like dividing the entropy by entropy at K200 and radius by R200, which is, yeah. And you get that the entropy profiles, almost all of them behave almost exactly the same in the outer part. As you can see here, you have R200 is where you have a 1 here. So all of the profiles there are very well behaved, corresponding, more or less corresponding to this power law relation here. And in the center, already in this early simulation, it was shown that effective effects from cooling, relative cooling, it was important in order to basically cool the gas and change, and that was changing the profile, but generally only in the core. More recent simulation, for example, here you see the Omega 500 simulations in the work of Lau et al. 2015. You see, if you look on the left-hand side, you see the entropy scaled by critical quantity, so 200 critical quantity. And you see the fact that these profiles are basically one on top of each other at many different redshifts. Here you see 0, 0.5, 1, and 1.5. And the main difference that you see is at very large radii. However, what also was argued in this paper was the fact that if you change the scaling to be not with respect to the 200 critical density of the universe, but with respect to 200, the mean matter density of the universe, then you get that all the profiles look way more the same up to much larger distances. And importantly, you also see that at large distances, you see that the entropy doing a downturn, because at very large distance from the cluster, the entropy that of the gas that you should see should be basically the entropy of the pristine gas, so a very low entropy in principle. And then when it's accreted, it increases, and then when it goes to the center and cools, it's going to decrease again. And the fact that you have these bounds here, so the fact that entropy goes up and down, is very useful because they can really be used to trace and determine a boundary for galaxy clusters. Because as it was shown in this nice paper by Ang et al. 2021, you really see in the simulation this sharp drop in entropy around simulated galaxy clusters. And differently from 200 mean or 200 critical, which are somewhat arbitrary definition, which are depending a lot on the gravity-only theoretical prediction, you can really use entropy to define actually the boundary of galaxy clusters. Okay, but coming back to the profiles, more modern simulation, like you can see here the recent TNZ simulations of many hundreds of galaxy clusters were simulated. You see that although in the center you see a plethora of different entropy profile, when you look at large radii, in particular when you look roughly around R500, which is this basically vertical line here, you have that all of the profiles of these galaxy clusters at large radii look like they are following this very simple gravity-only subsimilar prescription, even in these modern simulations. And that is also true in a different set of simulation, like you see here, for example, the 300 project, where they also go to a much higher redshift. They go to a redshift of 4, where the cluster there probably are like very tiny groups. But still there, you see that up to quite some decent redshift, upper redshift of 2, let's say, the first 3 lines here, the entropy profiles at large radii follow very closely the prediction from the self-similar model, which is this dashed line, this dashed gray line here. And differences between different sets of simulations were investigated quite a lot in the literature. For example, you see here a work in 2016 by Sembolini, where they compare different simulation tools on the same galaxy clusters, and they found that although the simulation tool may tell us a different entropy profile, entropy level in the center, when you reach R500 and R200, basically you get the same you get the same entropy profile. And the same was shown to be true in more recent simulation in the Oppenheimer et al. 2021, when they have this first set of simulations that all of them were kind of different in the center, but overall at large radii at R500, which is this value here and upwards, they were all following this 1.1 power law going up there. So just to summary up a little bit, what is the prediction that we expect from theory is the fact that overall, if you have gravity only, you should get basically just a simple power law of the entropy profile. So the entropy function of radii should be just a power law. And when you had some cooling or feedback in the center, you can have a plethora of how much this flattening level in the center changes. but overall the picture looks like a flattening there. And further on, other than having this entropy inversion that you can have here at super large radii, you can have some sort of flattening before that point because of presence of non-thermal pressure or presence of clamps are actually biasing the entropy profile that one, for example, can measure. And so this is just to give a summary of what theory is telling us. So when you look at entropy profile, when you look at its shapes, it tells us directly some connection with the theory behind it. And before going to the evolution of the entropy, it's important to establish some sort of baseline entropy profile that we can assess at low redshift. And I decided to start by this work from Cavagnolo et al. 2009, where they took basically all the clusters that were present in the Chandler archive at that time, so roughly 239 clusters, as it's written there. And they showed that the entropy profile, similar to the simulations, in the core, they have a lot of differences. However, look at the outer part, and they are all going to be very closely to this white line, which is basically the self-similar prediction, this gravity-only prediction that was already found 20 years ago. However, the issue with this sort of sample here was the fact that the selection function was not well defined. And so assessing some sort of systematic study was a bit harder. And this was made easy by selecting some clearly defined sample, for example, the REXEC sample, where they observed just roughly 30 clusters with XMM Newton at a very low redshift, so below 0.17. And they observed that up to the radii that we're able to measure, the entropy profile was following very well. Here, don't see much well, but you see there is a dashed line here below all of the lines. And all of the entropy profiles at R500 are all of them are very close to the prediction. But okay, you might remember in the plot from the simulations that deviation from this sort of self-similarity was mainly happening, let's say, at R200 below after R200. And here we are just talking about quantity within R500. And the reason why it was hard to go beyond R500 at that time was because with X-ray only, it's very hard to go beyond R500 because you need also not just the density profile, which is generally a cheap quantity to measure, but you need also a temperature profile. And measuring a temperature profile is very challenging. You need a lot of observation time. And so the feasibility of doing that for a sample is quite harder. However, with Suzaku, thanks to the observations of several clusters and thanks to the fact that Suzaku had a very low particle background, it really enabled the measurement of temperature profile and therefore of also entropy profiles out to very large cluster-centric radii. For example, it was shown after for many systems, like you see here, like almost a dozen, that it was really possible to reach measurement of thermodynamic quantities up to R200, which was at that time unprecedented. And it was noted at that time the fact that the entropy profile that was measured at roughly around R200 was showing some sort of downturn already. So it was kind of questioning the theory behind it, because the theory was predicting that this sort of upturn should happen much later in radii. However, it was pointed out later on using different techniques that was possible thanks to these advances of these new generation SZ telescopes, which enabled to actually do combinations of pressure profile from SZ telescopes, for example, Planck in this case, but it can also be done with SPT or with other SZ telescopes, and observation of density profile coming from XMM Newton. And interestingly, it was pointed out that in this case, you need to use the relation of pressure divided by density to the 5/3 to get the entropy. And it was interesting, was pointed out that depending what is the density you're dividing with, and depending how you derived it in particular, you are basically finding or not finding this sort of upturn. And it was shown the fact that if at large radii, you take, for each annuli, you are extracting your quantity. If you take the median of the surface brightening that you observe in that annuli, or you take the mean, you get a significant difference. And particularly using the mean, you get this sort of upturn that you see here in yellow, while if you use the median, that doesn't really, the downturn, if it happens, it's happening much, much less pronounced. And also this plot also highlights the fact that with X-ray, temperature measurements are only present within R500. And therefore, to get all of these data points here, it was really important. It's really important to couple that observations with SD observations. And this sort of work was extended in one of my PhD works on the X-scope galaxy clusters, also at low redshift. And what it was shown here was the fact that large radii, when you combine X-ray and Z information from XMM and Planck on this sample of very few but complete sample of galaxy clusters, you get that at large radii, your overall average profile doesn't really show already this downturn that was previously observed. And also in a recent review by Walker et al. 2019, when they compiled the list of clusters for which R200 was indeed achievable, either by combination with Planck and with a Z and X-ray or Suzaku, it was indeed shown that overall the low redshift clusters follow the overall general baseline up to at least R200. There might be some differences just a bit above R200 because, I mean, we don't know yet, but probably some uncertainty in the measurement. I mean, we don't know that. But below, within R200, we can really see that all of the profiles, although there are some scatter, of course, as in all measurements, they all follow nicely this baseline gravity-only prediction. Okay, so now that we established the low redshift baseline, we can look at how this profile evolved with cosmic time. And just a reminder for everyone that galaxy clusters at high redshift are very, very tiny compared to clusters at low redshift. And this makes them not just much more dimmer, but also much more tiny on the sky, such that the effects due to the PSF or some other effects like that are going to be very much more important than clusters at low redshift. So in 2014 already, in the SPT collaboration, McDonald et al. Already had a sample of roughly 80 clusters observed in SPT, and they measured the entropy profiles using stacking and ignored the first two columns, just look at the third, which is the overall entropy profiles not divided between different morphology of clusters. And you see that in the lowest and high redshift clusters, it looks like deviation with respect to the low redshift clusters and the self-similar model or the gravity-only prediction in this dashed line white, it was really small and not really much significant. And also in a early work that we did in 2017, we did similar work to how Cavagnolo did on the entropy profile before, but however, we did select the clusters to have enough exposure such that we're able to measure the entropy profile at large radius. So the selection function for this system was not properly well defined. And still, it was really hard to get even to R500, which is actually the right-hand side of this plot. And also here, R500 was basically also in this case the sort of the limit. And only later on, with some more dedicated follow-up observation, very long XMM observation and channel observation on high redshift clusters, it was possible to actually reach and go slightly above R200 using X-ray only datasets. This, for example, is the work by Bartalucci et al. In 2017, where they used 5 SPT selected clusters at redshift of about 1. And all of these cases, they didn't, I mean, even if they had a lot of exposure time, not many of them actually reached R500. And still, when the last data point that was measuring there, still the profiles were going very closely to the self-similar gravity-only prediction shown here by this white line there. I also got involved in the study of very high redshift, very high mass clusters in SPT during my first postdoc. And we studied there 7 clusters at very high redshifts. These are 7 SPT clusters. And other than this very weird flat entropy profile cluster, all of the other one show this sort of still increasing, and even this one slightly at high radii. They all show at very large radii entropy profiles which were very closely to the prediction of the self-similar model of just this dotted line. And by comparing this high redshift sample with low redshift sample, one can indeed get some measurement of what is the evolution of entropy profile at large radii with respect to cosmic time. And the self-similar model is predicting that the entropy profile at large radii is following the scale factor of U of z to the minus 2/3. And when you do that, measurements in the observation, like the work we did in this for this curve here, comparing that with the ACO profiles, we obtained that at large radii, we didn't even reach R500, but in the last data points we were able to measure, we didn't really find any statistically significant differences with respect to the prediction from the self-similar model, so the gravity-only model, which is interesting. And recently, thanks to NICA2 and other more precise, more high-resolution Z instruments, it was possible to measure entropy profile out of very large radii by doing the combination with X-ray, similar to how basically we did in X-scopes by combining XMM Newton and Planck. Here it was a combination of XMM Newton and NICA2. And the white line that you see here, it's where the prediction from the self-similar model is. And still, for this one case, it was only possible in this cluster at ratio of 0.9. You see that the entropy profile was measured quite well up to R500 and even a bit beyond, but still was following this self-similar prediction. This was also shown in a recent work when the combination was done by combining a Z from Planck and SPT and Chandra on these SPT clusters, also redshift of roughly 1. And you see here in white what was the measured profile. And in this dotted curve, you see the power law. Note that is not aligned because it's the x-axis is not in a log scale. And also they did the same analysis in along the minor and major axis, but still, even for those cases, the entropy profile at large radii was still kind of following this power law behavior that was predicted 20 years ago. And even, a bit more recently than that, but at the higher redshift, this cluster here was observed by NICA2 and by Chandra. And although there might be some significant difference in the center, depending on which center one uses, at large radii, they are all very close and all very close to the prediction that you see here in green, in dashed green, with the self-similar model. So to basically come to a point here, at high redshift, we don't have many measurements of entropy profiles beyond R500. And when you have at R500, they are still all in agreement with the prediction from the self-similar model. So this evolution here to the scale factor to the minus 2/3. Finally, one thing that I actually might be speculating myself, but I think it might actually be expected, was the fact that in a recent paper, Florian Ruppen et al., they combine ACTA, which is a southern hemisphere as this telescope, which has a high resolution, with SPT, and they combine that with SPT and Chandra to get very detailed measurements of the quantity of the entropy in the core of clusters and their evolution with cosmic time. Indeed, the goal was indeed to find a evolutionary sample here and to study the core properties. So I'm expecting that maybe they are going to publish or to prepare some result regarding the entropy profile at large radii, as it's really now achievable if they have the exact measurement for all of these clusters. And finally, I want to have a couple of slides of what Athena can actually tell us about the entropy profile and how well we can measure it at high redshift. So Athena has 2 instruments, as we all know, WFI and XIFU. And here you can see that a short 100 kilosecond WFI exposure on a cluster at redshift of 1, which is basically at high, basically very massive group or a very low mass cluster, as you can see here. You can get exquisite entropy profile out to very large radii. even at for cluster at redshift 1 with this low mass. And if you go at redshift of 2, yes, the uncertainty, of course, increases. But this prediction was done for a group of very, very low mass, just 3 times 10 to the 13 solar masses. So it's really a tiny group. And still you can get a decent entropy profile. And when you do that with a sample of many clusters, you beat the statistical uncertainty and you reduce the uncertainty on these profiles, and you actually obtain significant measurement of the entropy profile at very high redshift, even for these very low mass groups. And the same is also true for XIFU, although the analysis is done slightly differently, as you will know. And for example, even for a cluster at ratio of 2, I mean, a group of ratio of 2, which is a very massive group at ratio of 2, 7 times 10 to the 3 solar masses, you can get exquisite entropy profiling. You can even use at this very short observation, at this very high ratio, at this very low mass, to distinguish between one or the other entropy profile. And I want to briefly conclude my talk by briefly mentioning the fact that by summarizing basically what I've discussed here. So you have the simulation that predicts sort of baseline self-similar model up to R200, and below there might be some downturn, but we don't see that yet. We cannot see that yet in the data. And at low redshift, we are still fully in agreement with these predictions in basically all of their recent and more updated works. On high redshift, we are limited by the sensitivity of our instruments, and generally we're not able to go much beyond R500, and we are able to do it only for a couple of objects where combination of SZ and X-ray is possible. And finally, Athena, thanks to WFI and XIFU, is really going to revolutionize all the studies of high redshift clusters because of its sensitivity in measuring even entropy profile for this low mass at this much distance. And yeah, that was my presentation. Thanks.
Great. Thank you so much, Vittorio. That was a really, really, really great introduction to clusters in general and to why we want to measure these entropy profiles. I think I will recommend to all of my students to watch your talk if they haven't done it yet. This was really pedagogical, very nice. And also very interesting in terms of the newer results that you showed. If anybody has questions from the participants, may I encourage you to either, you can post them in the Q&A, or you can raise your hand, then we can allow you to speak. In the meantime, maybe let me be a little bit controversial, or let me poke you a bit with the question. So you showed that Athena, of course, will be able to go much further in redshift, much more sensitive, and much further in radius than before. But you've also shown that everything we've seen so far just follows the self-similar profile. So do you really expect that we see any surprises with Athena? Will these upgraded characteristics really let us probe new physics, or will we just keep looking at the self-similar profiles?
Yeah, that's a very interesting question. So, of course, when you go that's much lower in sensitivity, and what you find is can really be almost anything. But what I've shown here with all of these observations here at high redshifts, what seems to be found was indeed, yeah, all of these few individual clusters were kind of following this prediction from the self-similar model. So maybe that's mostly so these only are like a couple of clusters on which this kind of thing can actually be probed. But still, it's important to probe it and actually observe at some point this. I didn't put so much emphasis this kind of downturn in entropy, because that is really giving us a lot of information, not just on basically a physical radius of galaxy cluster, but the location where the entropy profile has a downturn has a very strong implication on the mass accretion rate of galaxy clusters, on how much mass they accrete over basically some time. And this is going to basically especially if you do that at high redshift, is going to basically to put a lot of fixed stones that then must be followed also by simulations, and that will also going to be probably very important in order to understand the overall structure formation, I would say. But yeah,
I fully agree. I would really love to see this downturn of the entropy, not because of the clumping and other issues, but actually to see it, the real physical downturn at the radii that we expect.
Yeah.
I'm not seeing, are people shy? I'm not seeing any questions. Don't be shy. Going once. Everybody's on May vacation. Going twice. Okay, seeing none, let me remind people that the next installment of this webinar series is going to be on the 3rd of July. Now I have learned that it will be a colleague of Vittorio. It will be also from Bologna, from INAF, and it's Mauro D'Adina, who will tell us about a new era for the study of UFOs in AGN. And UFOs are ultra-fast outflows. They're not actual UFOs. So let me encourage you to join us on the 3rd of July, and hope to see many of you then. And thank you very much, Vittorio, again for the really nice talk.
Thank you for inviting me.
Okay.